Yes.
So for the readings, is that the readings we're supposed to have done by this class, or is it
Except the first class, where that was not possible, yes.
Okay, so we should have had done 2.1 to 2.4, right?
The way you said that kind of is a subjunctive, like an as if.
Yes.
Yes.
Okay.
So Thursday you'll want to have read 2.1 through 2.4 and 2.5, 2.7, 2.9, and 2.10.
Okay. Thank you.
Sina, right?
Yes. This is going to be generally on the reading, like for the day or on the past?
So I think we discussed this on Wednesdays. Anyone remember the result of that?
The answer was that it's the reading for the previous.
Yeah, reading for the previous. So the stuff we've covered in class, basically, and the reading for that.
No, I just 2.4.
Okay. Did anyone have any problems in turning in the homework? See, I got yours, Sina. Everyone else need issues? Yes.
I just have a
Daniel.
question.
Yes.
So, I think the submission for this week's homework was in a image file format. Is that generally going to be the case, or are you specific? Because the syllabus says to turn it in as a PDF.
Image or PDF, either one is fine.
I have a choice.
You had to choose choice?
Yeah.
Okay. Yeah. I don't, either one is fine. Just again, don't do these very blurry pictures that I can't read. So, all right. One thing I wanted to cover about the demonstration that we did. Thank you very much, Mazda, for that. My wife enjoyed watching that tremendously. So just to keep in mind that what we did there was I changed the rewards over time. In fact, I hadn't realized until I watched it again that I thought afterwards, like 2 minutes afterwards, that he had just like raised his hands, and I rewarded him. But actually, he raised his hands a little bit, and I rewarded it, and then that caused him to go up. So the rewards changed over time. For a while, it was okay to just stand and face you, and that gave you rewards. But otherwise, over time, that stopped. And so we changed the rewards over time. Much better. And this was as an attempt to try and shape his behavior. So this is called shaping in behavior modification, operant conditioning, those sorts of things. All right, so there is a relationship between the sort of computer science, machine learning world of reinforcement learning and the psychological world of operant conditioning, okay, which is, there are in fact multidisciplinary workshops that are held to basically teach the folks from the other field what's going on in their field, because there's a lot going on with this. So in behavior modification, it's called shaping. In reinforcement learning, that's called curriculum learning. Okay, and the idea is, in order to learn something complicated, provide rewards to have them learn simpler things first. It makes a lot of sense. Curriculum learning actually isn't used all that much in RL. Normally what happens is we provide rewards, whatever the final rewards are, and you have to learn to do it. Okay? That works great for a lot of arcade games, for example. So there are a bunch of Atari arcade games for which reinforcement has worked very well in learning from the pixels on the video screen and being given rewards in terms of changes to the score that it learns to do human or superhuman play. But there are some games for which it works really poorly. Okay? One is Montezuma's Revenge. And there are a couple others as well, so it doesn't work well. And the reason is you have to do a lot of things before you get any reward. Okay? So we call that sort of a sparse reward environment. And it's like, you remember when Mazda was like walking down here and walking along the back and doing a lot of stuff and nothing was happening. Imagine, if that were the case, again, as I mentioned on Wednesday, if he had to wait until he did jumping jacks, right? There'd be a long, long wait before he learned it. That would be very hard. Montezuma's Revenge is kind of like just rewarding for jumping jacks and nothing else. Okay. Yeah.
Sorry, what these are shaping and curriculum learning?
Same thing. Same thing. Yeah, these are equal. Just different names. All right. We're not actually going to be doing any curriculum learning here. We're going to have usually an environment where the rewards do not change. Okay? And certainly not one where we're designing the change in rewards in order to shape how the agent learns. Let's just go ahead and do the quiz. This should be relatively straightforward. Famous last words, probably, but. And I'll get you one. Thank you. There you are. Thanks, Hina. Yeah, when you're done, turn it over. That may give me a good idea how many people are finished. Thanks, Sally. right, we'll give it another minute. You're going to be with the receiver, the quizzes, and you get to put the binder clip on. All right, can you please pass them to the right and then to the front? I want to discuss a little bit the homeworks. Symmetries. So the first question for the homework was, does it make sense to consider symmetric states the same? Right, so for instance, if we have Daniel, would you throw this away? So my goal in life is to get rid of marker. It's twofold. Get rid of markers that no longer mark or mark lightly. And the second is keep permanent markers away from whiteboards. So let's say you have this, and you also have an alternate, which is this, right? These are symmetric by rotation, right? Rotation, mirroring, and so on. There are different lines of symmetry. So should we treat these the same? That is, if I know the value of this state, should I assume that's the same value as this state? Give me a Garrett, or Garrett. Yes, that is you, Garrett.
So if our opponent is acting differently based off of treating the two differently, then our expected values would be different because our opponent might make different moves. But given that it's tic-tac-toe and we know that there's like an optimal policy that doesn't care about symmetries, then if we're just going for the optimal policy and we know that it should converge to that, then we can treat these two equally.
So I think the point you mentioned first is if your opponent doesn't view them the same. So if your opponent, I don't know, let's look at an example. So let's say it's, again, a beginner player that you're playing against. It's an O. And your beginner player plays an O in this case, but plays an O in this case. Then you don't want to treat these the same, right? You want to basically take advantage of the fact that your opponent is treating them differently. Because they are not honoring in some sense the symmetries that are there. If your opponent was honoring the symmetries, then yes, go ahead and treat this state the same. This state the same as this state, the same as the ones that are flipped horizontally and vertically, and so on. What's the advantage, Josh, of treating them the same?
Is that you'll probably converge to like an optimal policy or strategy?
Well, so if you don't treat them the same, are you saying you would not converge to an optimal policy?
No, you probably will still.
Yes. You still will. What would be the advantage of having?
Get faster.
You get faster because?
You have more examples, or you can better generalize.
Yeah, basically, if you hit this state and do something with it and update its value, and then hit this state and update its value, you are updating both states together with two updates, as opposed to if you treat them separately, you've only got sort of one piece of information about a game you played here and one for the state here. The other advantage is fewer states means less memory, right? This tabular method where we're keeping track for every single state of what our value is means we have less to keep track of, okay? And then the next one I wanted to group, so for greedy, let's see, let me try to remember exactly how the problem was stated. Something like, will a greedy algorithm do, let's just look at it. Yeah, so might a greedy player learn to play better or worse than a non-greedy player, Matt?
I thought that a greedy player would learn to
actions that seem better in the short term but end up being worse in the long term?
I would certainly agree with you that a greedy player can be short-sighted, right? If you basically have exploitation or exploration, and basically isn't looking at the big picture and can end up being exploited. However, you're comparing it against what? A non-greedy player who has foresight and plays well. Let me be a non-greedy player. Okay, and then the next play I go here and wherever, right? If I'm random non-greedy player, do you think you're playing better or worse than me? Probably better, yeah. So it depends on actually that non-greedy player and the status of that non-greedy player.
Is it called something
Yeah.
different if you like have, if you're not greedy but you have way better moves, like you're more likely to choose those? Does it have like its own name, or where it's like, this is probably the best move, but like occasionally you'll do the like not best move?
That is normally this epsilon greedy is the simplest case of this. Just 1 minus epsilon of the time, most all the time, play greedy, epsilon amount of the time, pick randomly. Do some exploration, and the easiest way to do that is randomly go. Yeah.
Does non-greedy imply random moves?
Non-greedy, so for epsilon greedy, epsilon of the time we do a random move. In general, non-greedy doesn't necessarily mean that it's random, which is why I was asking Matt, tell me about this non-greedy player. You know, is it a good one or is it a random one or something else? Remind me your name.
I'm Sean.
Sean, S-E-A-N?
Yep.
Okay, all right. So now on to the last question, which I would expect to not be straightforward, okay? So the question was, when you're making these, right, most of your moves are exploitation moves. You're making greedy moves in tic-tac-toe. Some of the time, let's say epsilon of the time, we're going to do some exploration. When we do an exploration move, should we back up the value from the state we end up with to the state before? Because that's normally what we were doing, is as we make an exploitive move, as we go to a new state, we have its estimate of the value, and we back that up to try and update the parent's estimate of the value. And the question was, in an exploration move, should we do that or not? And what happens if we do and if we don't? Let me show an example. So let's say we have this state here, right? Our greedy move is what? We guess we'd learn our greedy move is to go here, right? We do some random stuff, and this one always seems to work so well, right? Because what's its reward? 1. So if we started out with this as a reward, let's say of 1/2, and we happen to choose this, and this is a 1, then we would basically backward propagate some of that 1 up to here. So 1/2 would now be, depending on sort of what our rate of learning is, 3/5, might move itself up to 4/5, might move itself up towards 1. Okay? But some of the time, we want to explore. Let's say we explore by looking at this one. Okay? That's going to take us to a new state. Not exactly sure what the state is, because it depends on what O does, right? If O happens to go here, then we have a value of 0 here. And the question is, for this value of 0, do we want to propagate it up to here? And I'd say no, right? If the value right now is 1, because we played this one a lot of times, and now we explore playing an x here, and we get a 0, do we want to reduce the value of this state? And I would say it depends. Once we train our agent, how are we going to play is the question. When we finally go out and play in the real world against the tic-tac-toe, championships at elementary school or preschool or whatever that is, then what's our algorithm going to be? Are we going to be fully greedy, or are we still going to be epsilon greedy? If we're going to be fully greedy, what's the value of this state? Mazda. It's 1, because what do we know we do? We act greedy, we play this one, we win. This is a 1 every single time. So the value of this state is just as good as the value of this state. Does that make sense? If, on the other hand, when we go into the championships, we're playing an epsilon greedy, then is the value of this state 1? Mark.
I'm sorry, can you repeat the question?
Yeah, so if we are actually going to play, once we've trained this all, in an epsilon greedy fashion, that is, we're going to sometimes still do exploration, is the value of this state 1?
No.
No, because some of the times we're going to lose, or we're going to end up in a draw. Okay? So it depends whether you want to be propagating this back or not. Whether you're going to finally, whether you're trying to estimate what's the value of this if we act greedy versus what's the value of this if we act epsilon greedy. Now if we take an exploration move, like here, right, this is an exploration move, and let's say O doesn't play here. Let's say O plays here, okay? Then we've got another move, right? So we take an action, and eventually we'll get to an end state. Is this action going to be greedy or not? Allie. We know this one was non-greedy, right? It was exploratory. Is this one going to be greedy or exploratory?
So
Okay.
by taking like the right side would be exploratory.
So because this is the greedy choice,
Right.
and the fact that we choose this one must have been because it was exploratory.
Right.
So this happened epsilon
Yes.
percent of the time, or epsilon proportion of the time. So now we play this one. Now it's time to choose another action. Is this going to be a greedy action or a non-greedy action?
Non-greedy, because we would have to take the non-greedy choice beforehand. Is that?
And that's not quite. What actually happens is every single time we choose an action, we're going to flip our coin and say, did epsilon come up? If epsilon came up, we'll explore. Otherwise, we're going to be greedy. So we would most likely take a greedy choice here, and a greedy choice here, and a greedy choice here on the way. And so therefore, we would update these states. Okay? Because these are states we could get into. And what happens if we act greedily? We want to go ahead and update those values. So it's not once we start a branch, we don't update anything along the branch. It is only a step where we do the exploring that we don't update.
Is there like
What am I meaning?
Oh, Justin, sorry.
Justin.
Is there like a standard or like normal epsilon we would like to use? Like a
0.1, 0.01,
Okay.
something. We're going to look at some graphs and see, what happens and what the trade-offs are. Mazda.
So my understanding of, I guess I'm a little unclear on how the back propagation works and whether we continue all the way down until we reach an end state and then back propagate all the way back up.
We're going to talk all about
Okay.
that's
The other
kind of
question
Monte
is-
Carlo versus temporal difference. This is just our brief introduction to it.
Okay, got it. But either way, we never back propagate against exploration path, or for one leg that's an exploration edge.
It depends how we're going to be using this agent when we deploy it. And so it depends. You had a question, JD?
That was just my question.
Okay.
I was wondering if you went back, how far you back.
Yeah, that's all this question of Monte Carlo, temporal difference, and then this sort of K-strap, in-step bootstrapping, which is a combination between the two. That's what we'll all get into. So, all right, so let's talk about bandits. What is a one-armed bandit? Pascal, are you here? You are not. Yeah, that's it. There's Pascal. Daniel, a one-armed bandit, do you know?
I think it's a slot machine.
A one-armed bandit is another name for a slot machine because, right, it has that one arm there. You can choose, and it takes away your money, right? So, by extension then, we have K-armed bandits. K-armed bandits, basically, we have an agent who takes an action. The environment is this K-armed bandit. The action is which lever to pull. So it's, 1 to K. and we get out a reward. Okay. So for our purposes, let's say the reward is positive, although it need not be. In fact, let's not even say that. But in the normal slot machine, let's say you're paying a quarter to play, it's often negative 25 cents, negative 25 cents, negative 25 cents, $1.50, right, when you win something, negative 25 cents, negative 25 cents. So that's one way the bandit could work, the one-armed bandit could work. Or we could just look at it as, let's say you prepaid. You know, you bought 100 pulls on the bandit up front. And now we're just going to look at what reward are you getting as you go. When you have a slot machine, it has a certain payout that it uses. Right? We can imagine some mean of a slot machine of what it returns. And if we had 4 different slot machines, and I told you they're all set up with different means, that's a K-armed bandit situation, a 4-armed bandit. And you would want to, well, let's look at an example. So here is bandit app, okay, with 3 arms. You get 100 pulls, prepaid, I paid for you guys, okay? What I want you guys to do, is you get to play this one time with 100 pulls. Okay, you're going to play it in groups of 3, 2 or 3, let's say. And your job in your group is to get more than anyone else with this total number right here. So I'll just go ahead and try one. So I click on the blue, and I get a payout of 4. And I click on the blue again, and I get a payout of 5. Right? So it shows you what your last payout was, and you have your total. This is the number you're trying to increase. Okay? So spend about 5 to 10 minutes, I guess, spinning your 100 pulls carefully. Do not refresh. Do not play again. One time is all you get. You can get to this from the schedule, or it's
My strategy, I'd say we try is completely random. Yeah, uniformly random.
okay, and kind of keep track also as you're going, because I'm going to want you to reflect on what you were thinking as you went. Okay? So maybe you want a scribe to keep track of what's going on, but I'm going to ask you questions afterwards. You can do this on a laptop. You can do this even on your phone. I tried it. It works.
I mean, I don't know.
That could work. I mean, I just thought, like, I feel like because we don't know any of the probabilities, like,
Yeah, so that's what I think. Feel like if you're like 10, 15 trials for these ones, see what we got most out of, then make that one then go all the way. I don't know. I'm like, it's just like how many.
I actually am going to give you this piece of information. Each bandit is stationary. That is, there's a probability distribution for each one of these, and it will not change as you play. Okay?
So is that how many tries we should get for each ring? So it's like a bunch of one. Then we have 100 tries. And I just made up 50. Just like
Brings out the spreadsheet. All right.
That's like completely random. The trying times.
sorry.
Oh no, don't worry.
Yeah.
I like it. Choose the smallest screen you can.
Okay, we can try 15. So we'll do bandit 1 first, 15 cuts. 1, 2.
Yeah,
Alright, I'll go slower.
And it would be curious to hear what you wish it had kept track of for you and logged.
Okay, so next one is bandit 2. So 1,
So it's just
Right now,
Sean? Okay.
It went from 43 to 85.
Let's give us a 42.
But no negative.
No negative.
Okay, you ready?
I said never negative, and then I stopped, and I pulled it back.
We got 140. Yeah.
Lost 25. Okay, and we got
All right, half done.
That's like basically minus like.
I guess I suspended 3 all the way. Let's see what we got.
Okay, ready?
What do you got? Dude, that's not. 362. So your average per poll is 3.6. Yeah. Okay.
3.42.
All right, you guys are gonna have to hurry it up. 342. So your average per poll is 3.4. Okay. And what did you end up exploiting one of them? Yeah. Which one?
Bandit 3.
All right, start exploiting. We need to finish up soon. Hey, I can't tell you ahead of time. There's no targets to shoot for.
If we figured out the problem.
Yeah, I mean, if we have the exact probabilities, I mean, if they can do that.
All right, start pulling those. You get another 30 seconds to get your final total. You don't want to end this wasting any.
I'm curious what would happen if we used the right number two.
We used 45% of the votes to try out that deck.
All right.
42% of the total.
Is everyone finished? Finished? You guys still look like you. Did you guys finish? And you guys?
Yeah.
Okay.
That's pretty good, actually.
All right.
Definitely got more.
So let's start. Julius. First, I'm just curious what your total was.
329.
329. All right. So some people are happy, some people not so happy. Tell me about your process and what you guys were thinking.
Oh, so the first 10 rows, we kind of just wanted to explore what the behaviors are for each of the 3 bandits.
So you spent 10 total doing that, or 10 for each?
10 total.
10 total.
10 total. Okay.
And then we got a hunch of we found out that Bandit 2 had 1 and 10.
Okay. Bandit 2 has 1s and 10s.
Yeah. So and then Bandit 1 kind of had somewhere consistently 5.
And
4.
4. And okay.
Sometimes it did like -20.
Oh, that's nice.
Yeah.
Okay.
And then 3 had a 2, 3, and 25. Yeah, 2, 3, and 25. Always positive.
Okay. So you spent 10 and you did some exploration. You didn't find out all all of these numbers with 10.
Well, so
Did
we
you?
did like maybe 20 or so, like evenly, and then we decided bandit one seemed to be the best, and so we kind of started doing that a lot, and then we got a negative, and then we got straight.
Because you were surprised
Yeah.
all of a sudden. Okay. All right. Your name is?
Nick.
That's right. So Nick and Josh, tell me.
We're on two different teams. It was Josh and Matt, and me and Garrett. I'm sorry.
All right. Josh and Matt. All right. Go ahead, Josh. Or Matt.
276.
276. All right. So what was your process?
So we were trying, so we did like the first, 10 rolls, doing one of each, and we realized that like, oh, B gives 10, so we started doing that one. And we were like, oh, maybe we should also try A, because that's giving us like 4th and class, so that might do well. And we got a minus 20 on the A, so we were like, we're not going to do that one again.
Okay, minus 20, it's like, no, don't want that, okay? Okay.
And then we also were like, oh, what if, C also has, or like 3 has like a magic high number, and we cut that and we hit a 25 a couple of times.
And so then what did you?
I just went back and forth between 2 and 3.
You went back and forth between 2 and 3. Okay, so your exploitation was don't use 1. Okay. Nick and Garrett?
Yeah.
Garrett or Gareth?
Garrett.
Garrett.
We got 304.
304, all right.
So we spent the same kind of thing doing the first 10. We did like 3 or 4 on each one to try and get an estimate of what was going on there. And then we started out by going for the 1, and so we hit negative 20, and we're like, uh-oh, so obviously we'll go 2. And then we got 1 15 times in a row, so we're like, okay, maybe this wasn't actually as high of a probability as we thought. So then we went back to 1, because we never explored 3 enough to find out that there was a 25 in there.
Got it, okay.
It looked like it was just basically
2, so you did, okay.
There.
All right, now what information, by the way, would you have wanted besides what's the last payout? Right, if you could have had some other statistics here besides just giving the distribution.
Possible payouts?
No, I'm not going to give you that. So Josh, you were keeping a spreadsheet. What that the spreadsheet could have kept track of would you have liked it just to have shown? The history.
We did average and standard deviation.
Okay, so average and standard deviation. So if you had seen what the average so far was, that would have been helpful. Is that right? Yeah. Okay. Your name?
Nelson.
Nelson. And you worked with the people in the front row, right? No, you worked with Daniel and Mark? Mark with a C?
Yeah.
Okay. Tell me about, first off, what'd you end up with?
351.
3 have a new high. Okay. Any particular different? What'd you guys do? I know you ended up exploiting late in the game.
Yeah.
Yeah, I mean, we did that, right? Yeah, it was pretty simple. We ended up just like spamming yellow the last like 7 years.
Okay, you did yellow. Or the right one? Okay.
Yeah.
All right. Do we have anyone higher than 331? Your number?
362.
362. All right. So what'd you do different, if anything?
Well, we did like 10 of each one, and then we didn't get the 25, but I predicted that you would have a high number somewhere. So I was like, there's got to be a really high number somewhere, so we kept doing 3 and then we got it, and it was all 3.
That is not just I just object to that meta analysis. Okay. All right, and you guys got
342.
342. All right. Any other things you guys wanted to say that you thought would be useful?
So
Alex.
instead of like doing each 10, we did each 15 and we saw all the numbers. So
And you saw all the numbers.
Yeah.
And did you also? So did you end up exploiting yellow or the right one?
Yeah.
Yeah, but
Okay.
like since we gave like a little bit extra to like explore, we like saw everything
Got it.
before we decided.
So in one sense, it was good because you got to know about yellow. In the other sense, you spent a total of 30 of your clicks on these things, or polls, or whatever they are. Wait, your name?
Varun.
V-A-R-U-N? Okay, Varun.
kind of think it's deterministic, the sequence, because we tried it a few more times and got the same.
I don't understand how that can be. I mean, I clearly said, do not refresh and do not try again.
After we got our initial score, we then went back and got 4.
Okay. Well, so that's a good point. What you guys should all say is, oh yeah, these guys were lucky, right? They happened to get a random number generator that gave them more 25s than anybody else got, right? That could be, right? That can't be? Why not?
We were noticing the same sequence.
Yeah, it was deterministic. I set a seed. I didn't want you guys complaining. Yeah, our luck of the draw, these guys, they got different flips. No, it was identical. And it didn't matter, in fact, even in what order you chose these. They each independently have their own sequence that they use. So it didn't matter that you happen to choose blue first and then yellow would give you less 25s or anything. So anyway, I know all of the arguments people make. So I had 4 kids and yeah.
Is there like a way to maximize it? Like what's the maximum score you can get given this?
Well, what else do you need to know besides what the possible values are?
Which order they are.
I guess which order. What else?
How frequently each.
Yeah, you want to know. So this was 50-50, I think.
What?
No? Oh, someone bring up the code for it. You have the HTML? Yeah, it's a nice little React app. So what is it?
It's 80-20.
Oh, it's 80-20. That's so close to 50-50. And this is, I think, 45-45, 10? Yeah. And this one is 40.
0.5, 0.4, 0.1.
0.5, 0.4, 0.1. Yeah, so anyway. And you never know, right? It could have been that any one of these had a 0.001 chance of giving plus 1,000 or minus 1,000. Unless you look at the code, you can't know. So, all right. So that is the job we're dealing with in dealing with K-armed bandits. So you don't know what these distributions are. You do know each one of them has a mean. And assuming that you're trying to maximize your expected value, which of these should you choose in general? Ali, I already chose you, didn't I? We'll skip. Sina. If you knew the means, which would you choose?
The highest mean.
Yes. That's what we're trying to do, basically. Find the highest mean and choose that. And we may have to choose other ones in order to get our estimate of what the means are. Okay, so to begin with, that's all we'll do is we'll just estimate the mean. So we could say something like, let's make some definitions. We'll say A of t is the action at time t, and R of t is the reward. Okay? So we can define Q star of some action, which is the actual expected value. So this will be, let's say, the expected value of R sub t given A sub t equals A. Why t here? What if this instead of t were, I don't know, 1? So the expected reward at time 1, given at time 1, we take action A. Is that the same as the expected reward at time 3 if we take action A, or time 5 at action A? No? Yes?
Isn't it
Nick?
if you assume the distribution is stationary, that we should assume?
Yeah. If we assume, so given the distribution is stationary, then the expected value for RT mean, they're all the same, I guess is really what I want to say, right? The same expectation. Our estimate is going to be different. So our estimate is going to be capital Q sub t of A, right? So that's going to be estimated, our estimate at time t of what? So this is actual, mean, and this is estimated. And this is like pretty simple. Look at all of the rewards we've got for having chosen A so far and take the mean of those. So just the summation from I equals 1 to, let's say, t minus 1, because we haven't acted yet. Okay? And the terminology here in the book is basically just say, well, it's the reward at time I, but it's only the reward at time I if we took this action, right? Some of the rewards were for different actions, and we only want the ones for this action. So we're going to use all right, so 1 with some predicate is equal to 1 if predicate is true, right, and 0 otherwise. So it just gives us a 1 or 0, a nice way to basically just pull out all of the appropriate rewards. And we divide then just by the number of times we've taken that action, which, again, the book uses this nice notation, again, of the ones. So just so this is called what, a characteristic function, I think. So this is the total rewards for action A. And this is the number times chose action A. You will find we don't end up doing very complicated math in this class. Okay, it's all pretty straightforward. So if you guys had, in your spreadsheet, you kept track of that, right? You kept track of both the mean and the standard deviation. And it still was confusing me because people in 2 different rows were shaking their head, but you're on the same team, right? So that gives you an estimate of what the mean is. So the greedy action would be choose the one with a higher mean. We do have to make one modification here, and that is if the denominator equals 0, choose a default. Like maybe 0, right? So if we did this, well, let's define something. So let's define in let's see what I want. Yeah. So this is going to be number of times we chose A from 1 to t. So if we just keep track, I'm sorry, let's look at it the most simple way. We'll just keep a list, let's say, of all the rewards for each action. And every time we need to calculate this, just calculate the mean. Okay? That would work. That's a little bit slow and memory intensive, right? In the sense of if we've chosen action A 1,000 times, we've got a list of 1,000 numbers in there that we need to take the mean of. It seems like more information than we need to keep, right? If we can instead keep a running mean, we can go ahead and store much less information. So let's look at that. Let's make some definitions for a moment. We will come back to this. So let's look at R1, R2, and I'm going to put in super A. The book doesn't bother doing this. But so this is the first reward for action A. And the second reward and the third reward and so on. So we're looking at it focused on a particular action. And now what we can look at is looking at Q. And if we look at QT of A, right, that equals basically this sum. Well, let's just look at it this way, right? That's R1A, R2A, all the way up to RTA. Okay? So this T is now going to be with respect to choosing A. Right? It's not across all A's. This is just for this particular A. Dividing by T. Yes? See, you guys let me get away with this. T minus 1. But we can rewrite this recursively in terms of T minus 1. So let's figure out how to do that. Yeah.
So it would just be the previous reward we had, so Q of T minus 1 over T minus 2. Let's see. So if we keep a count of how many rewards there are, then we can use, like let's say that we have 8 rewards, then it would just be the previous reward divided by times 7/8 plus the new reward times 1/8.
Okay, let's look at that. So let's just think about this. So we got 7 numbers here. You know, R1, R2 to R7, and then now we're adding in an R8. Okay? If we kept this as a mean, this is QT minus 1 of A, right? And so we want to end up with somehow this plus this divided by 8, right? So if we multiply 7/8 times QT minus 1 of A plus 1/8 times R8, that equals QT of A. Yes? Okay. So let's work on that a little bit. In fact, I wish I hadn't erased that. So we had 7/8 times this. Let's just see whether this does it. Let's call it, right, this is going to be 8. Actually, this is just going to be T minus 1, right? Times qt minus 1, rt minus 1 minus qt minus 1. Let's see if this makes sense. Say it again. We want to end up with t minus 1 as our numerator, as our denominator.
Oh,
Right? And so therefore, if we look at this, we're going to basically take this reward and divide it by t minus 1. So that's its fraction. And then we're going to have qt minus 1 minus qt minus 1 over t minus 1. Right? So in the case where t is 8, we have q7 minus 1 Okay, why am I getting confused here?
Shouldn't be T up top. Because it's QT.
So let me make sure I'm using the same terminology that we use in the book. I apologize for this. Oh, let me bring up a aid. So text. Why is that lecture 2? Sorry for a moment. All right. And so this is correct. The difference in the book is they're looking at basically, they use n instead of a. So if you use n plus 1 here, this will be n. This is all the way to n. This now becomes all right. And there's just a little bit of algebra between here and here, okay, like a tiny bit. So this gives us an incremental update on q of n plus 1, where we basically say, what's the old value? What's our old mean? And then we will add in, we're going to call this a step size, and then our current value and our old estimate. This structure is going to be very common. We take the difference between what we think is a better estimate and our current estimate. We multiply that by some step size, and we add that to our old estimate. What we use for something is going to change. For instance, we'll change this 1 over n eventually. Okay? So this just gives us the mean. Okay? What do we need to keep track of? We need to keep track of what our current estimate of the mean is and how many times have we visited this. Okay? So that's going to be n of a and q of a is what we'll keep track of those. What do we want to initialize the mean to? Arbitrary is right. Yeah, we're going to actually look and see that it it actually is going to matter what we set it to. On Wednesday, we're going to look and see that if we are optimistic and make the values high, then that will encourage some exploration. But we could just set it to 0. So if we set it to 0, the first time we take an action, action A, we're going to say, okay, take our old value of 0, add that to 1 over n, which is 1 times r. So we initialize basically q0 of A to be equal some constant, but let's start with 0. And then once we've actually visited it, then we get a true estimate, right? Because q sub 0 is going to go away. So let's look at an example of a 10 armed bandit. Right, in this 10 armed bandit, they basically set up 10 arms and randomly chose a mean for each arm. Okay, so the mean of each arm was chosen with mean 0, standard deviation 1. And then once they had a mean, the distribution is around that mean with a standard deviation of 1. So it's a normal distribution. The bandits don't have to use a normal distribution. Their reward can be whatever distribution they want. But there is a mean. Okay? This is just useful as a test bed for seeing the distributions are the same and kind of being able to visualize them. Right? So in this case, if we use this 10-arm test bed and we had 100 presses and we knew this, what would our greedy approach be? Right? If we had this extra information. Kaki? Yeah, so if we knew this information about what this was our 10-armed bandit test bed, what would we do to get the most reward?
We would choose the action with the highest.
Which one?
3.
3. Yeah, we choose action 3 over and over and over and over again, right? But as you just played, you know you don't know that. You have no information. So you've got to do some exploration to find that. So we'll randomly choose some. We'll come up with some means. We'll greedily then choose the one with the highest mean, except some of the times we'll explore. And that may cause us to decide a different mean is better. So in the example of our 3-arm test bed, if you chose the left one first, unless you were unlucky and hit the minus 20, you would have a positive value, and all the others would be 0. So what would you start choosing? That. Except you'd say, well, some of the time I should try these others, right? And so as you try those others, you might choose number 2, which gives you a 1. Say, no, my number 1 is still better than this. You might choose number 3, which gives you, 2 into 3 or something? So you might still go back to 1. But eventually, you're going to epsilon greedily get yourself a big bonus in number 3. And then that will update your mean, and you'll switch over to number 3. So this shows the average reward at a particular time step. So this was done by taking this 10-armed bandit, running for 1,000 steps. And in order to deal with, they didn't just fix a random seed, because that wouldn't be fair. Right? Instead, they ran this 2,000 times with different seeds, different runs, different random numbers, different values that come out for the epsilon greedy, different values that come up for the environment, too, as to what the reward was. And then just average them. So what you see is, at time step 1, the average reward is 0. Why would that be? Sean is somewhere. Let's hold it. Don't help me. Go ahead. Go ahead.
Do you have any moves yet?
Well, you actually, time step 1, you make a move. And we're saying the average reward for making a move is 0 in that 10-armed test bed. Why would that be?
If I was thinking you got nothing back.
Well, so let's look at this example. So this was one environment. These means are all chosen at random, centered around 0, right?
Yeah.
So basically, we could pick any one of these, and the average of them all is going to be 0, especially as we go across 2,000 different environments. So that's why we get a 0 to begin with. And then we start being smarter, right? And getting more and more. And you can see that the epsilon, non-zero epsilon, gives us better reward. We do more exploration, as you can see here. Does that make sense? Why is the blue line higher than the red line? Daniel. Closer, Daniel. Daniel Yang.
I guess because like the early exploration allowed it to get better policy earlier.
Exactly. That's exactly it. Yeah, did more exploration, found the better one. And then this shows how often a policy chose an optimal action. And you can see here the greedy algorithm basically was under 40% of the time was it an optimal action. And these guys are increasing. This one, which should end up with a better optimal action in the long run, a lower epsilon or a higher epsilon? Will here? Jake?
The lower one. That one.
This one should end up with a higher percentage of optimal action?
Eventually.
Because?
Because once it does find the right one, which would take a longer amount of time, it will choose it more often.
Yeah, once it finds it, which eventually it will, it'll choose it more often. Right, it'll spend less of the time in that exploration, a wasted exploration. But you can see the long time is a long time.
Do they ever have an epsilon that like changes?
Yeah, you could certainly anneal, have a schedule for your epsilon, but it changes over time. Yeah.
Is there like an epsilon where it's like
Remind me your name again.
Oh, sorry, Justin.
Justin, okay.
Yeah. Is there like an epsilon where it's like past the point of no return, where it's like exploring too much and then that's affecting it? Could it go like this, but then like start to go down over time, or?
I don't think it'd ever go down over time. I'm trying to think of what an epsilon 0, like 0.5 would give us here. And it would basically, right, there'd be an asymptote at roughly 50%, let's just say, because half the time is wasted, it's wasting time. It's slightly more than that, because some of the wasted time is actually still picking the good one, right? But we should just asymptote up to that.
Okay.
That is what I would expect. So we could choose an epsilon large enough such that we asymptote below the greedy, right? So this is our bandit algorithm. Where we keep this running mean. We initialize Q and N to 0. And then we just loop through. Who is not familiar with argmax? So you know max. Right? Max returns the maximum value. In this case, we return the maximum Q value, right? Argmax says return the maximum A that corresponds to the maximum value. So it basically returns the index. So this will return us an A that's the maximum. There might be more than one that's maximum, right? Maybe you have 2 with identical means or 2 with estimated means that are the same so far. We just pick one of them. And then with probability epsilon, we pick a random action. We, let's say, call the bandit, which gives us our reward. And then we update the number of times we've taken this action and our new estimate of the mean. Pretty straightforward. Questions at this point?
Earlier you said we might end up changing the set size from 1 over n of a, but wouldn't that be the set size that gets us to the true mean? Why would we ever do something else?
So if we had a non-stationary problem, for example, we would prefer to weigh recent rewards more than other rewards. So that's one reason. And in practice, we are going to end up just using a constant here, which will give us, and we'll talk about this on Wednesday, an exponentially weighted average. Okay, we just go to the homework.
So this doesn't, this simple algorithm doesn't seem to account for our discussion earlier about not updating during exploratory steps. And I'm getting the sense that there's certainly a reason that this is a slightly different problem, but could you elaborate?
Yeah, so here's the deal. We talked about in the case of the tic-tac-toe, where when we took an exploratory step, we didn't update. We don't have states here in this simple bandit case. So in the case of the tic-tac-toe, we had values for each of the states, and we didn't want to update our estimate of the value for a state. Here, all we're trying to estimate is the value of actions, and anytime we take an action, we're getting useful information. Right? So whenever we take a step A, even if we were exploring with a random action, we still are getting a better estimate of that action's value.
So is this more of like evolutionary algorithm in that sense, or is that a different thing? Like in the sense that we're not really referring to a state, but just evaluating the policy?
Well, we don't have a state because there are no states in this problem because it's simplified, because we want to reduce the complexity of it so we can just look at this. So in this particular case, every piece of information is useful information, and it doesn't really matter whether we got there via exploration or exploitation.
So I think that Brett mentioned there's a way to change this into a full reinforcement learning algorithm. Like what modification would you have to make?
Well, we have to take into account state, basically. So we are going to be looking. It's better that we wait until we actually get into the full reinforcement learning problem, and then look at how we can do it. So, but we can do this same idea of just, instead of estimating the value of an action, let's estimate the value of a state and action. So every time we've taken the state and the action, what have we seen in terms of not only current reward, but long-term reward? And just update that. That's the kind of the short answer. So Wednesday, we're going to talk more about the bandit algorithms. We'll talk about a different approach than just the greedy approach that basically takes into account how much exploration have we actually done on this. Focus exploration on unexplored actions. And then we'll also do the programming, hand out the programming assignment. I'll be in the cafe until 3.